We are back with Experiment 18 Part 3, and as you can see, the circuit board is pretty much bursting at the seams here in terms of components. In fact, I pretty much ran out of extra leads here and had to start cutting some that actually fit the short lengths that I needed. So you'll also notice I have an extra tool here hooked up to the circuit so that I can more quickly analyze the pins in these chips. This is called a logic probe. This also actually is a pulsar, but I haven't really played around with it too much on that side. You can use this to actually send out signals from these little posts on the handle. But anyways, that aside, I'm going to use this tool to help us analyze what's going on with this circuit. And last time we left off, we basically did not have the 555s in place. So this guy, that guy, and that guy are all 555s. And these are our 4026 decade counter chips and our 7-segment display. So actually I will keep this in my hand for a moment. So you'll notice that this first 555 has a wire bridging pins 2 to 6. And for those who watched previous videos, they should be familiar with this setup. This is your astable mode. So what this is doing is it's basically when powered, it's constantly oscillating. And the one in the middle is actually wired in a new configuration we haven't seen before. This is called bistable mode. And what this does is it sets up this 555 to act as like a giant flip-flop. So it's either, outputting or not. And the 555 here is actually set up as a monostable, which was the first way that we actually used 555s. So we've literally got 3 different modes: astable, bistable, and monostable, and each of them function differently. So the monostable, I guess I should have also said, is responsible for when you push a switch, it sends a single pulse based on your push. So what we're going to do is have these work in unison so that when we trigger the monostable, it has a built-in delay, and that's the time needed for some of the capacitors to charge up, namely, I believe, let's see, yeah, this one. And once this charges up, it sends a pulse through this little ceramic here, and this guy is a tricky bastard. He made me spend a lot of time, and you'll notice over here I've got a second 104 ceramic, and I have a little story to dive into on these. But before I do, I will continue here with just explaining the basic setup that we have. So once the signal gets sent through the, well, not really through, but the pulse that's coming out of this 555, let me correct myself. So this 555 is normally high on the output, and when you push the switch, it goes low, which makes it sink the current from the cap, which actually makes the pin 4 of the second 555 here go low, which triggers the flip-flop, which starts this whole chain reaction. So there's quite a lot going on, and to be honest, it's almost impossible to explain all of the nuances of this circuit in a single video like this. So what I will do is fire it up, show what it does, and then we will kind of just start touching some pins with the logic probe and get a better feel for it. And the goal here for this guy, before we had the counters, which would, pretty much just like you push a switch and it would count every time we pushed. Now we're actually going to have a reflex type thing, except I didn't sub in the parts that would make this thing count so fast that you couldn't see it. I left it at the standard about 4 pulses per second, so you'll see what happens. And there is room for improvement on this circuit, because you'll see when I start to power this thing up, let's see if I can actually get that to, there we go. So as I power this thing up, you'll see it's already counting before I even do anything. So like there's a definite room for improvement, because you know, if you were going to try to make a little reflex timer type device, you wouldn't want it counting before you even had a chance to, you know, say go. Alright, so we're up to 9 volts, and as you can see, it's just counting. And once it gets to 9999, it should cycle. Yep. So anyways, all I'm going to do is push this button to stop it, and this to reset it. So we're zeroed out, and the idea is when you push this button, hopefully you guys can see that, because that's kind of hard for me to... Alright, there we go. So if I push this, it's going to have a delay, and at some point it will trigger this light to go hot and that to count. And so the idea is when this goes hot and this starts counting up, you're supposed to quickly push this switch to test your reflexes in terms of time. And this doesn't seem very informative, because you know I could go like this, keep my finger on the button, and probably get a 1 or a 2. But the idea is to replace some of the parts so that this is counting in milliseconds, and that way you could probably measure up to you know I guess 1 second, because 999 milliseconds, if it was any longer, it would cycle over again and you wouldn't know how many seconds it took. So that's the goal of the circuit. So now for the fun part, this is not an audible based logic probe, just has some lights, so I will try to point it up if I can as we analyze some of this. So right now the circuit's kind of frozen, right? So the pins that are of interest to me, the ones that really tell us anything, are going to be basically pins 3 and 4 of these chips. 4 being our resets. So right now, I don't know if you can see, this is high on the monostable, on the reset, and low on the output. So right now, this is essentially sinking current on pin 3. Now, if we were to push that, push the switch to start this process, let's watch what happens to pin 3. Goes hot. Now once the cap starts charging and it finishes, it's going to go low, as you just saw. It went low again. So now you'll notice it didn't actually continue to count here, and that's probably because some of the current was being absorbed through the probe. So if I push that again, without the probe in the way, it does continue. So you have to kind of watch out for a little bit of interference with your other devices at play here, because there's just a very small amount of current at play with this little ceramic discharging, because this is a 104 ceramic, which is what, 100 nanofarads, so it's very very small. So we basically shown the output behavior of that first 555, which was the monostable. Now we're on to the bistable. Now this guy's interesting, so I will touch the reset first. So he's high right now by default, and his output is also high. So if I touch this switch, he's still hot on the output, and now he went low when the switch went live. So, and while the switch is live, reset's still high. So to kind of repeat and summarize, so the bistable was originally high or hot, however you want to say it, on the reset pin and the output before anything happened. And then once the first cap here charged up and the signal was sent from the first 555, the pin 3 of the second 555 started to sink current. Now, why is that important? Because if we look at pin 3 of the second 555, we've got basically a path from power through the LED through, and one path goes from that this brown line right here all the way to pin 3. So really, when this 555 went low on pin 3, it started to sink current. So that's what lit up the LED. And at the same time, when this is sinking the current, pin 2 of our most significant number on our 4026 chain also received a signal to pin 2, and I think, is that the clock enable, was that the counter enable, or hold on one sec here. And pin 2 is, I think, yeah, so that's disable clock. So basically power is running through here to the disable clock pin. So the last most important of all is the astable 555 right here. And what he's doing is actually very, when I looked at it with the Logic Pro, I was like, this is kind of inefficient, but nevertheless, let's just analyze what it's doing. So by default, without the circuit doing anything, just frozen in time, our reset pin is hot, and our output is, what do you know? Look at that. It's flashing between high and low, really fast. Well, not really fast, but about 4 oscillations per second. So you might be asking yourself, well, why is it doing that? There's nothing going on. That's kind of the point of the astable chip. No matter what happens, this guy's always doing that. So like, if I keep this on the output pin and I push the switch, or the switch right here, and watch. So once this guy goes hot, I'm just keeping my eye on the flashing lights here. Nothing really changed. And every flash that we get here is a count here. Well, truly, let me rephrase that. Every other flash here is a count, because you wouldn't have a count on a high and a low. You'd have a count on the corresponding high. So yeah, and the reason for that is the output of this astable 555 is going into pin 1 of our 4026, and pin 1, as we know, is the clock input pin. So every time it gets a hot pulse, it's like, oh, I better up the counter, and that's what causes this guy to step. So even if I stop it, we know that this astable is still sending pulses. The only thing is the chip is actually disabled because of pin, the 4026 chip is actually disabled because of pin 2 right now. So it's disregarding the fact that pulses are being sent to the clock input. So that's definitely cool, but there is definitely more than one way to skin a cat when it comes to this circuit, and I could definitely imagine this astable chip just sucking up a lot of power for no great reason, just because it's always running. So definitely room for improvement on the circuit. Okay, so I think we pretty much explained most of what's going on, and this was definitely a very challenging project for me. This took many evenings of just kind of doing, a little bit at a time, especially when you run out of the pre-cut wires. It just takes a while to put this thing together. But the most challenging part of this circuit was back to, let me turn the circuit off since we're done with this now. Alright, so this is just a typical 104 ceramic cap, as is that guy right there, which was responsible for signaling from the output pin of our monostable to the reset pin of our bistable 555. Now, what's interesting is I first used this capacitor, and I wasn't able to, once I turned the circuit on, it was counting, but once I stopped it and reset, and I was ready to start it again, the counter wouldn't start because the second 555, the bistable one, wasn't getting getting enough of a pulse to actually flip. So the light never came on and all that stuff. And it took a while. At first I thought that there was a problem with this capacitor, and I was kind of going part by part, trying to figure it out. And I even hooked up my oscillator to the cap, make sure, or not my oscillator, I'm sorry, my oscilloscope. I was just kind of wanting to see what the waveform of this charge looked like, and I thought for a moment that, hey, maybe there's something wrong with it, and switched it out, and just no avail. Then I decided to switch this cap out with another one, and it worked, and I was thinking to myself, wow, do I have a dud or what? And I put my multimeter on diode measurement, or not diode, capacitor measurement to check the capacitance of this ceramic compared to this one, and this guy only, so he's rated as a 100 nanofarad, but he was only actually holding about 89. And this guy, who's also rated 100 nanofarad, was holding about 130. So it turns out that for those of you who do try this experiment, make sure that you actually have a cap that is at or over the rating, not under. Because if it's under, you are not going to get enough of an AC pulse when the pin 3 of the monostable goes to sync. You're not going to pull enough of the current away from the pin 4 of the bistable to trip the reset. So yeah, that was a major pain to figure out, and I'm glad I was able to. Definitely learned some interesting lessons there. Oh, and another thing that's very curious, I've gotten used to seeing the capacitors in line and used as a filtration mechanism for AC current, but what I haven't seen yet, this is the first circuit I've seen it, is by default, actually, you know what? I'm going to turn this back on for 1 second, show you guys something. Power it back up to 9 volts, and you will see, okay, we're at exactly 9, let me kill that guy. If we use our probe one more time, one thing that's interesting is both sides of this ceramic are both receiving power at the same time. So this happens when it's hot, so let me push start. Let me just let it go. Okay. Oops. One thing I don't recommend, don't short the pins together with your probe. Actually, let me reset this, make sure I didn't mess anything up when I just did that. Alright. Let me let him go again. Okay, there's a state where I was pretty sure there was. Let's see. So right now, the pin 4 of the bistable is high, and the pin 3 of the monostable is low. Now I remember there was a state where both of them were high, and I'm trying to find that again. I think it's during the charge. Yeah, see, that's high during the charge up. At the same time, that's high. And that's the other, oh, I just shorted the pins together. It caused this to trip. Heh, interesting. Saw that? It picked itself back up. So the point I was trying to get at is when you push that first switch to start this process, while the cap's charging, both sides of the ceramic cap are actually positive. So literally there's no charge in the cap. It's like tension on both sides fighting each other, so there's no charge that can really store in there. So trying to visualize what that means when you've got an inline cap with power on both sides, that was a first for me. But once this guy starts to sink current, then it becomes evident that you're going to have a slight push away from pin 4 of the bistable, which makes it go low and trips this whole process. But if this ceramic is not big enough, then you don't have enough pressure, if you will, or voltage released from the pin 4 of this guy to trip the flip-flop essentially of this bistable. So you got to make sure you have a big enough one. And the other thing I was trying to figure out was, hey, do I have any more polarity insensitive caps, or whether it's a ceramic or otherwise, that are larger, so that I could just go above and beyond the need in terms of value. And unfortunately 104s right now in my stock hold are the largest I have, so I was sitting there hunting and pecking trying to find one that was actually bigger than the 89 nanofarads that we had on the first one. So keep that in mind, guys, and good luck with this, because this is a challenge of a circuit, but it's quite quite pleasing once you finish it, because this is a fairly intense circuit to build, and you learn a lot from it. Not just obviously the 7 segments and the 426, but you also pick up a third mode on the 555s, and if you happen to have a probe handy, these are also going to get a good workout on this circuit, because the odds of this thing working on the first shot are probably pretty slim, but you never know. So that's it, and I will see everybody on Experiment 19.